Now we will see the Boolean algebra. This is our next topic in the course, Boolean algebra. Before we begin with Boolean algebra, it is good to have some introduction to gates. Logic gates, these are used in building digital circuits. These are the building blocks of digital circuits, and there are some gates. We will see all those gates now. And here we can see some table which is having all the basic building blocks of digital circuits called gates. Let's begin. In this column, the name of the gate. Here we have the symbol of the gate and the functionality that that particular gate accomplishes and its truth table. Now let's see what are these gates. Gates are functional building blocks of digital circuits. All the digital circuits, however complex the circuit may be, that is made out of these gates. These are the fundamental gates in digital electronics. We build all the complex circuits. However the complexity may be, those circuits are built out of these gates. Now let's begin. This is called AND gate. It is the symbol for the AND circuit. AND circuit contains transistors and so on. And here we are not showing the circuit. We are showing just the symbol. This is the symbol of AND gate, which has two inputs. This is one input called X input. This is another input called Y input. Y input, and this is the output F. That output is written here. That output is equal to X dot Y. It is AND operation. X dot Y, the dot is AND operation. So X and Y are ANDed, and the output is the result of AND operation of X and Y. And here we see the truth table. Truth table means the behavior of the AND gate is shown here. Truth table generally means the behavior of the circuit is shown in the form of a table in which we show the output, and that output corresponding to what input combinations. In the truth table we present all the possible input combinations, and for each input combination we also write the output. Now let's see, X and Y are the inputs, F is the output. Let's understand the AND gate. If you understand one gate, then you can easily understand other gates. There is some terminology involved here. There is one circuit called AND circuit, and for that circuit this is the symbol, and it has two inputs X and Y. It has one output F, and the operation that this symbol performs is written here, F equal to X dot Y, where dot is the AND operation, X and Y, or you may read as X dot Y or X and Y. Now let's see, X and Y are inputs, and what are the values for these inputs? They are not decimal inputs, they are binary inputs. Means X can take either 1 or 0, Y is also either 1 or 0. You are not free to give any value to X, like 45 volts, 25 volts, something like that. X takes only 1 or 0, like this, 1 or 0. Here 0 means not necessarily 0 volts, 1 means not necessarily 1 volt. 0 means it is a voltage range. 0 means low logic, 1 means high logic. There is a voltage range for low logic that varies with technology. Now you may think like this, 0 means 0 volts, 1 means 5 volts. For now it's okay. 0 means 0 volts, 1 means 5 volts. 0 means low, 1 means high. 0 means 0 volts, 1 means 5 volts, like that. So X takes only two values. Only two values are allowed for X. What are they? 0 other one is 1 or high. These are the alternative names. What are the alternative names for 0? 0, low, 0 volts, all mean same. For high, for 1 or logic high or simply high or 5 volts, they are all one and the same. So X takes one of these two values, either 0 or 1. Y also takes either 0 or 1. So we have written all the possible combinations and also given the output of this gate for each of those combinations. Now let's say x0, y0. X is 0, y is also 0. If you apply those inputs to the AND gate, what is the resultant output? 0. 0, 0 if we apply, what is the resultant output? 0. If x is 0, y is 1. X is 0, y is 1. What is the resultant output? 0 again. And for x1, y0, for this particular combination, for x1, y0, what is the output? Also 0. For x1, y1, then only output is 1 or high. If x is 1 and y is also 1, then f results high or 1. So how do you understand this? How do you describe the functionality of this AND gate in one line, in just one line? AND gate output is high when both the inputs are high, 0 otherwise, right? When both the inputs are high, only then f gives us high value, otherwise it produces 0 output. So if you want the output to be 1, then you need all the inputs to be 1. If one of the output is 0, any one of the output, if one of the output is 0, right, then the output is 0. That is the AND gate, its symbol, its functionality, its truth table. Here it is x dot y. That is the algebraic function. This is how we represent the functionality of AND gate in expression form. This is the expression form of AND gate functionality. Here the functionality is described in the truth table manner, in the form of truth table. Now let's see another gate. This is called OR gate and its symbol is shown here. It also has two inputs, x, y. It produces output f. Its algebraic expression is x plus y. This plus is OR operation. This is the OR gate. This plus is OR operation, x or y, and dot is AND operation. Here dot indicates AND operation, plus indicates OR operation. AND operation is also called product, binary multiplication or binary multiplication. It is binary addition. Now let's understand the behavior of this OR gate. Here we are not showing any circuits. This is not the circuit. It is only a symbol which represents the circuit. It is difficult to write the whole circuit here. Instead, we make some symbols. This is a symbol of that circuit called OR circuit. And this is the OR gate. Now let's see, x and y are the inputs. Just like AND gate, it has two inputs, x and y, and f is the output. And x is a binary value. X takes 1 or 0, y also takes 1 or 0. If that is the case, how many possible combinations that are there for x and y together? 4 combinations. X can be 0, y can be 0, x0, y1, x1, y0, x and y both are 1s. These are the only possible combinations. You cannot think of some value for x and y other than these 4 combinations. If you try, you cannot, you will fail. Now let's see, if x is 0 and y is 0, what is how our output is defined? 0. R produces output 0 for this input combinations, for this input combination. If both x and y are 0, then output is 0. If x is 0 and y is 1, the output is 1. If x is 1, y is 0, then also output is 1. If x is 1 and y is 1, the output is 1. Now, how do you write down, how do you describe the functionality of OR gate in one line? The output of OR gate is 1 if at least one of the inputs is 1. let's see, if at least one of the inputs is 1, then output of OR gate is 1. Otherwise, if all the inputs are zeros, only then output of the OR gate is 0. Next, another main gate is inverter. It is called, its a symbol is shown here. It takes only one input, unlike AND gate or OR gate. It takes only one input and produces one output. And let's say X is the input and this is the symbol and F is the output. So here is the truth table. X0, for X0, what is the output? If you apply 0, it inverts. Inverts means if you apply 0, what you get is 1. Or if you apply 1, what you get is 0. It inverts the input and produces the output. So for 1, you will get 0. For 0 here, you will get 1 here. So that is the functionality of inverter. And this is the expression. If you write this on the paper, this is how you write it. This is the X complement. We say X complement. We call it X complement. F equal to X complement or X bar sometimes. Now buffer, it is the symbol of buffer. Buffer just gives out the output which is the same as the input. Buffer here means it powers the input signal. If the input signal is weak to drive the load, then we use such buffers. We use this type of buffers. Buffer doesn't alter the input. It allows the input as it is at the output, but it gives strength to the input signal so that it can drive the load better. So F equal to X. What is the output? Whatever you put here, that comes out as it is with high strength, with high power. That is the meaning here. So buffer doesn't alter the input. It provides strength so that the input can drive the output load. So X, this is X 0 and its output is 0. If X is 0, output is also 0. If X is 1, output is also 1. So in general, F equal to X, that is the buffer. Next, Nand gate. This is the Nand gate. Nand gate is nothing but, first of all, you perform AND operation. This is the operation, AND operation. And then this bubble means this bubble is used for inverter. Okay. Perform AND operation for X and Y inputs. And to that result, apply inverter and inversion. That is what is called Nand gate. And it is a symbol of the Nand gate. This is a symbol of the Nand gate. Now let's see. There is a truth table of the Nand gate. For input combination, if for the input combination 0 0, output is 1. For 0 1, output is 1. For 1 0, output is 1. For 1 1, output is 0. Now let's see the difference between AND functionality and NAND functionality is just inversion. For which combinations we have output 0, for those combinations the output will become 1. For what combination the output has 1, for that particular combination the output becomes 0 in NAND circuit, right? Otherwise, if you want to describe this NAND functionality in one line, what would be the line? If at least one of the input is 0, then output is 1. If all the inputs are 0, or if all the inputs are 1, then only the output is 0, 1 otherwise. That is also equivalent statement, right? And its expression is, what is the expression? What is the expression for this gate without this bubble? It becomes AND gate, and the expression is just XY. And since we have added bubble to the result, so take the XY result and add complement to it, or take complement. Complement means if you get 1, convert that into 0. If you get 0, make it as 1. That's what it is. Next, another gate is called NOR gate. Another gate is called NOR gate. This is the symbol. The first, this much is OR gate symbol, and after adding bubble it becomes NOR gate symbol. This bubble indicates inversion. So perform the OR operation for this inputs, and to the result add complement. Okay, add inversion. So this is the truth table. For x0 y0 output is 1. For x0 1 output is 0. For 1 0 0, for this combination 1 1, the output is 0. So if all the inputs are 0, then only NOR gate output is 1. If any of the inputs are 1, if any of the inputs are 1, then output is 0. Output is 0. And for reasons that we will describe later, these two gates, NOR gate and NAND gate, are called universal gates. The reason is this: by using these gates, you can realize all other gates. If you have only these gates, NAND gates and NOR gates, you can build any logic, even AND gate, OR gate, all such logics can be realized by using these two gates called NAND gate and NOR gates. For this particular reason, these two gates are called universal gates. Other gate is written here. What is this? Exclusive OR gate. Exclusive OR gate. And write down first the OR gate and add one curve here before it. That becomes the exclusive OR gate. So its functionality is described here. 0 0 for the input combinations. For the input x0 y0, output is 0. For input 0 1, for input x0 y1, the output is 1. For input x1 y0, output is 1. x1 y1, output is 0. Means if you follow this, if you look at this truth table closely, you can say that if both inputs are same, doesn't matter whether they are 0 or 1, doesn't matter, irrespective of the inputs, if they are same. See here, x is 0, y is 0, or x is 1, y is 1. If both inputs are same, then the output is 0. If inputs are same, then it produces low output. Low means 0 output. If inputs are different, like if one is 0, other one is 1, or if x is 1, y is 0. If inputs are different, then output is 1. Output is 1 or high. That is what is exclusive OR gate. And the operation for exclusive OR is x. So this is the actual expression x y bar plus x bar y. Y bar is y complement. F equal to x y bar plus x bar y. Since it is not, it is burden to write this whenever it is needed to write down. So we have given one expression here, one symbol here, x exclusive OR y. There is a plus here, and which is circled, which is encircled. So if you have to write x y bar plus x bar y, then you write just this symbol x y. So x exclusive OR y means the same thing, x y bar plus x bar y. Next one is exclusive NOR equal exclusive NOR. Exclusive NOR. See, exclusive NOR, his symbol is much like the symbol of exclusive NOR is much like exclusive OR. Here at the end we have added a bubble here. This is called bubble. That bubble represents the complement or inversion. Now let's look at the truth table of it. If x is 0, y is 0, output is 1. X is 0, y is 1, output is 0. X is 1, y is 0, output is 0. X is 1, y is 1, output is also 1. Now see, now what you have understood from this truth table, if both are same, if both inputs are same, Doesn't matter whether they are 0 or 1. If both are same, if both are same, then exclusive NOR gate produces high output for 0 0 or for 1 1. When these two, when both the inputs are same, either 0 0 or either 1 1, the output is 1. If inputs are opposite, then output is 0. That is the R symbol. That is the exclusive NOR, not R, exclusive NOR. These are the basic building blocks which are used to construct complex circuits in the digital